Hey everyone, this is a solution to question 7. So we have a box supported by two springs, and we're told that it has a negligible weight, so we don't need to include a body force at C. We have two horizontal forces applied to the box here, 1 kilonewton apiece, and we want to free body the box and solve for the forces at A and at B. Okay, I'm going to go ahead and get the instructions out of here to simplify my screen. Okay, all right, the first thing we need to do is our free body diagram. So I'm going to dial back the loading diagram. And for my free body, I'm going to draw a picture of our lovely box of negligible weight. And of course, I want to include these two forces, each 1 kilonewton. And I'm not in equilibrium yet, right? So I am in force equilibrium, but there is a net moment on the body that is causing it to rotate this way. Do you see that? Okay. So I know I'm going to need some forces at A and B to keep this in equilibrium. And as I think about the nature of that rotation, like I can see point A really wanting to lift up vertically, and I see point B wanting to compress that spring. Okay. And if you can visualize that, you may be able to come in here and deduce right off the bat that we have a push force at B. And if I've got an upward force at B and the only other force in the system is at A, then this one needs to be a downward force. And again, let me just rotate this one more time so you can kind of see. So if those forces weren't there, right, B would be moving down. Spring B is pushing back to keep it in static equilibrium. So that's how we can think about that. All right, we've got our free body. That's all there is to it. Some professors are kind of sticklers about including all the dimensions, but for me, that's less critical. And the axes themselves are less critical for me. Certainly don't mind them if you want to pop it in X and Y, but if X is rightward and Y is upward on your paper or screen, most reasonable people would assume it was that way if they're not told otherwise, so I'm okay with that. Let's see, in terms of the dimensions, so I'm kind of picking up on this problem testing me on force couples. So my horizontal force couple is 400 millimeters spaced apart, and my vertical force couple is 300 millimeters spaced apart. And I'll keep the notation for our unknowns S sub A and S sub B and go from there. Okay, this one's going to be real quick. I know that my net moment on this object has to be equal to 0, and this is a moment about Z. And since I have two force couples, 1, 2, they must produce equal and opposite moments for static equilibrium. So the moment produced by the 1 kilonewton forces are 1 kilonewton of force times 400 millimeters, distance between, and uh, yeah, I'm going to go ahead and convert to meters. And it's not right or wrong to keep it in millimeters or so, but for this problem, I just kind of feel like meters is more appropriate. So, okay, so we've got this much moment, force times distance. Assess the sign by inspection. The 1 kilonewton forces tend to rotate the body clockwise, so we can give that a negative sign. And our next term, so S sub A and S sub B, that's my unknown force. So I'm just going to say S, the spring force, is equal to the spring force at A equal to the spring force at B. And by the way, it would also be okay to use an N sub A. If you had set this up with an N, that's okay. If it was an F for force, I would marginally be okay with that, right? We're trying to use more specific. notation for our forces and statics compared to physics, but I would be okay with that if you just used F for force. Okay, let's see. So I've got S, there's my unknown force that I'm solving for. How far are the forces spaced apart? 0.3 meters. Okay, and based on the assumption in my picture, I have one going up, one going down. Based on that assumption, that tendency to rotate is counterclockwise, thumbs up, positive. So that one gets a positive sign. Set that equal to 0, solve for the algebra. 0.4 divided by 0.3 is 1.3 bar. 0.4 divided by 0.3 is 1.3 bar, same as 4/3. Okay, and what that's telling us is the magnitude of that force, right? And so the directions as shown on the diagram are correct. Okay, so that is the answer. And when we, express that to 3 sig figs, right, we're going to do, say, 1.33 kilonewtons. And when we're asked specifically about S sub A versus S sub B for final answers, we would say something S sub A equals 1.33 kilonewtons down, S sub B equals 1.33 kilonewtons up, right? And these ups and downs are relative to our free body of what the box is feeling. Now, one other thing, so a lot of times when students are new to statics, they don't draw that free body diagram. Oftentimes, new students to statics would have drawn this. So you draw this, you'd be like applied force here, and a lot of students likely did this, okay? So we have unknowns S sub A and S sub B. And now we like in this assumption, we don't have a couple moment. Is it possible to still get to the solution? Absolutely. But you've got to write two equations and some moments about C here. So here's how you would set that up if if you weren't able to use qualitative equilibrium to deduce the directionality correctly, and you deduce them both up or both down, you can always run through the math. The math will correct you. Just watch your signs. So summation of forces in the y direction equals 0. So we have SA plus SB is equal to 0 based on what we see in the free body diagram. And by the way, if you've set this up and you get to this point and now you realize, oh, wow, I've got an issue, I can't get to equilibrium, do you have to erase and start over? No, you don't. Just keep going with the same assumptions. So summation of forces in the, oh, no, sorry, summation of moments. So I don't need to run forces in the x direction because it's already in equilibrium. So summation of moments about any z-axis is equal to 0. And the only reasonable place for me to sum, let's see. So what I'm thinking is that I've got two unknowns, S sub A and S sub B. And I'd like to sum moments anywhere along those lines of action, okay? The way I structured this problem, I really wanted you to focus on the force couple and couple moments. I didn't give you this measurement right here. So if you were going to sum about A and B, what you would have to do is introduce a new variable. You could call this distance, I don't know, L or L sub Y or whatever you want to call it. You'd have to invent something there, and then that term would be in both of your moment arms, okay? But you could also just pick a better point. So the best point that I see for doing this moment summation, it's going to be either this one right here or its partner over there. So I'm going to pick this one arbitrarily. And we need a label for it. Okay, so again, if you do your moment about a point that's not labeled, that's 100% fine with me, but please label it. So when we go to check your work, we know how to check your moment equilibrium equation. So I've got A, B, C, D, E. F is for force, so I usually skip that. So I'm going to call it point G. The summation of moments about G is equal to 0. Okay, and now we just do our regular old moment summation. So first term, I've got 1 kilonewton. I have a distance of 0.2 meters. That force tends to rotate the body clockwise, thumbs down, negative about G. Next term, I have another 1 kilonewton force. It is located at a moment arm of 200 millimeters or 0.2 meters, and it tends to rotate the body about point G, negative clockwise, thumbs down. So this one is negative. Okay. By the way, do you notice, so when I draw these in the picture, I'm doing that as a teaching aid. Do not draw them on your free body because it looks like an applied moment and that's a concept error. So I sketch them while I'm teaching, but notice that I'm always careful to immediately erase. Okay, so if you were to turn this in and like you had a big couple moment here, you're going to get a concept error on your free body diagram because there is no couple moment there. We're just doing a moment summation operation. Okay, next term, S sub B. How far away is S sub B from G? And so I just measure 0.3 meters. And then for a sine, S sub B tends to rotate the body counterclockwise, positive thumbs up, so give that a positive sign, and set it all equal to 0. S sub A is coincident with G, that's why we picked that point. So we wanted to solve for something. And I've done, goodness, I've done enough equations and calculators in my life that I would just stick with this and run it through my calculator now. So watch what I do, and my hope is this will help a few of you work faster and not harder. So -1 times 0.2, so that's -0.2. And then I want to subtract another 0.2 and hit equal. And so I've summed up, and for this problem, right, we could do some of this stuff in our head, but that's okay. I want to pretend like the numbers are more complicated, so you're using your calculator anyway. So that negative 400 e minus 3, or 0.4, we're using engineering notation in the class, remember, equals that summation. So I want to move it to the other side. So in my calculator here, I just multiply by -1 to get it to the other side of the equation. And now I divide by 0.3. Divide by 0.3 equals. And my conclusion here is that S sub B equals 1.33 kilonewtons, okay? Because the meters got canceled out when I did that division, and that leaves me with nothing but kilonewtons. The sign I got was positive, and what that means is that it confirms that this direction is correct. All right, now here's the tricky part. So we've got one answer done. Now we have to go back in and solve for S sub A. So I want to plug this into this equation. I'll change over to blue. So we have S sub A plus 1.33 kilonewtons equals 0. Therefore, S sub A equals minus 1.33 kilonewtons upward, okay? So at this point, I got a negative sign. That means that my assumption that the force was a push force going upward was wrong. So in terms of your final answer, all you need to do to correct that is say, so S sub A equals 1.33 kilonewtons downward. That is a very, very clean way of telling your audience that your assumption was wrong and put it in the right way, okay? So final answers, that's why I like final answers with magnitudes and the arrows, because you could have set this problem up with 2 ups, 2 downs, an up and a down and an up. So there's like 4 different possible solution paths, but as long as you're watching your signs, you will get to the right answer in the end, regardless if you did this assumption, this assumption, this assumption, or this assumption. I hope this was helpful. Thanks for watching, and bye.